Carlos Gamez with Metal Fatigue Solutions is our next presenter, and he's going to present on repair and load rating verification by detecting structural damage.
Well, good afternoon. My name is Carlos Gamez with an A. Also, I'm happy to present to you a topic that is not related to emergency repairs, actually about repair and load rating verification by detecting structural damage. So first, I'm going to give you an outline of what my presentation is going to be. I'm going to give you about a background on the current state of steel bridges. I'm going to talk about also the electrochemical fatigue sensor, the new technology that we using to detect structural damage and verify repairs like retrofits, and also I'm going to go over on how it actually works. And towards the end, I'm going to present field study that we did with this technology, better than me. But as you know, the U.S. has over 600,000 steel bridges, and 40% of them are at least 50 years old, and almost 10% are actually structurally deficient. In order to rehabilitate these bridges, it would require a lot of money. So usually what we do, instead of invest in a lot of money in repairs, one way to go around that is actually posting the bridge. So we limit the amount of load that it can actually support in order to preserve that bridge, in order to make it last longer. What are one of the forms of damage that can occur in a steel bridge? Well, one of them that we're actually going to be talking about is about fatigue cracking. Recently, the big companies are trying to increase efficiency. So what they do is actually, they say, well, let's put more loads in our trucks. They have a little concern of what do they actually do to the infrastructure. So one of the, once they do that, they actually, the result of that is accumulation of cycle loads and heavier loads into the steel bridges, make them to fill sooner than expected. So the first step to find or monitor cracks is by visual inspection. So we go to the bridge, we send a person to either using binoculars or from very far away and trying to detect all the fatigue damage or fatigue crackings that a bridge has. But a study has shown that 90% of those cracks are actually missed by visual inspection. And 30% of the areas that are called that have cracks, they're not. Now that we have identified cracks, so what do we do next? Do we know that it's actually active or it's actually dormant? So usually what we do is just wait for the next inspection period in order to mark where the actual tip is, and to report back if it is actually growing or not. Or if you put a drill stop or put a retrofit on it in order to arrest the crack propagation, we have to do the same thing. So we have this technology called the electrochemical fatigue sensor that is going to give you that information in a matter of minutes or days, depending on the loading going over the bridge or the structure. So what is the electrochemical fatigue sensor? Well, the EFS NDT method, that it can determine accurately if a crack or a fatigue crack is actually actively growing or not. It can also detect microplasticity. That is a precursor to cracking. It can also immediately verify efficiency of repairs and retrofits. One thing that you can do is make a plan of what retrofit to use or what repair you want to use, and instead of deploying that fix to the whole bridge, you can actually test it and how effective that's going to be. You can have different set of fixes and see which one is more cost efficient, and verify with this technology if the problem, in this case fatigue cracking, is being solved by those. So how the EFS works. The EFS works very similar to a medical electrocardiogram. It reads electrical signal coming from the bridge. How do we read that electrical signal from the bridge? So what we use is a sensor that, and we put some electrolyte in it, and we apply a constant voltage and read back a current. So you see, if you can see in the picture on the bottom on the left-hand side, you will see the steel in the bottom, and the electrolyte is in the form of marbles or balls. And then we have a passivation layer. That passivation layer is created by the electrolyte and the constant electrical current that we put into it. What the sensor reads back is once this passivation layer has been broken or stretched out. As you can see in the part, in the second part of that figure, you will see that a crack has been formed. When a crack has been formed, a new steel is being exposed. That makes the electrical signal change significantly. And once it's been exposed, the passivation layer reforms again. And this goes back and forth, back and forth. The passivation layer breaks when you have a significant loading and the crack is growing, and reforms again when the load is actually come back to what it was. What is the EFS system consists in 4 major components. The first one is the sensor. And if you can see in the picture on your right, you see 2 pairs of black plastic on the bottom near to the drill stops. Those are the sensors. In this case, they are the short-term sensors that they're made to last up to a year. The other one is the data collection hardware. That is the gray box that you see on the top right of the picture. And the data analyzer, that is the software that analyzes all this electrical signal coming from those pair of sensors. That is actually not shown in the picture, but it's that black wire that is connected to the gray box that is somewhere else near where the inspector is. And the wireless communication, so you can monitor or assess the activity of the crack remotely. So the first component is the sensor itself. It's made out of a non-conductor casing, a liquid electrolyte that is put inside of the cavity, I think stainless steel mesh that provides the voltage to form the passivation layer and read back the current coming from the sensor. The sensor on the top, like I said, is the short term. It's made out of foam. It's made to last up to 10 days. And you have ducts that you can use to put the electrolyte in the cavity, and so that way you have the formation of the passivation layer. In the 2 pictures on the bottom is the long-term sensor. These sensors can actually be made out of any shape to fit anywhere in the bridge. They're usually custom made, so they are not necessarily flat. The picture on the bottom right, you will see 2 of them, a pair of sensors. One of them is actually the one on the left, the one that has the red wire, is the one is installed on top of the crack, or nearby where the crack should be propagate to. And the one on the right is actually the reference sensor. We need 2 sensors in order to know if there's actually a crack activity. So why do we need that? It's because the passivation layer is really sensitive, so we'll also pick up elastic deformation. But when plasticity or a crack, the opening of the crack is occurring, that electrical signal is significantly different from the signal that you get from elastic deformation. So by comparing those 2 signals, we can say if a crack is actually growing or not. So then we have the data collections hardware. That is, in this case, that black box that precisely controls the EFS sensor array voltage and measures the current flow from the 2 sensors, or how many sensors you have installed in installation. And also it stores all the data on an SD card, so you don't have to babysit the system. So you can just let it run and come back from the data, or retrieve that data wirelessly. The data analyzer is the one that does pretty much the job, and it's going to tell us if the crack is actually growing or not by comparing those 2 signals. And when we compare those 2 signals, we have what we call the energy ratio of a crack. The energy ratio of a crack is the area under the curve of the sensor that is on top of the crack or near the crack over the area under the curve from the reference sensor. We have thresholds for that, so if it is from 1 to 1.5 ratio, the crack is not actually growing, it's actually just experiencing elastic deformation. If that ratio is from 1.5 to 1.9, it's showing microplasticity, a precursor to crack propagation, and above 1.9, the actual crack is actually actively propagating. In the picture on the right, you will see that the, I don't know if you can read it, but it says time signals in the time domain. you will see that all those peaks that you see in red actually corresponds to actually a really heavy truck going over it. So the pattern of this signal resembles very closely to what a strain gauge is, and a strain gauge reading will be. And also you see the green trend line, that's the reference sensor. You can see they're significantly different. But in order to see this a little bit better, we actually do represent that in a frequency domain. That's the last picture on the bottom. You will see that the red line is significantly bigger than the green line, meaning that in this particular case, the energy ratio was 5.04, meaning that the crack that we inspected during this monitoring job was actually significant. The EFS on an actual field. So we have a project in the Arizona DOT in the I-15 river bridges where we actually inspected 4 different structures. And in those 4 different structures, we had 19 locations were monitored with the EFS, 15 locations had visible cracks, and 4 retrofit locations were actually inspected as well. These locations were actually selected by the ADOT and the team actually executing the project. EFS Installation Example. In this case, as you can see, is the short term sensor. That's why it's a white foam. And it was located on a longitudinal crack in a girder web near the top of the flange. As you can see, the first step to install this system is to remove the paint to make sure that the electrolyte is in direct contact with the steel. In the pictures, we actually put all the notations in there, like a crack length, location, and the date when this location was inspected. And also at the end, when the crack is being removed, the whole thing gets repainted again, so we don't have corrosion problems or any other problems with the asset owner. Well, now that the EFS has been installed, so what do we need to do in order to get some data? Well, we have 2 options pretty much: ambient traffic or do a roll test. If roll test is actually an option, that will give you the results right away. If you use ambient traffic, we have to wait for a significant load to go over the bridge in order to get an accurate reading from the sensors. But in this case, we actually did both. We gathered data under ambient traffic and also roll test. For the roll test, we used 63,000 pounds in weight, and we used 2 different speeds. One was 5 miles per hour and 65 miles per hour. What were the results of this test? Well, the first one is the roll test at low speeds did not provide usable data. When the vehicle goes very slow, it will actually, the way the passivation breaks and reforms, it's kind of quickly. So if the truck or car is going very low, the sensor will detect it as almost like a quasi-static loading. So the passivation layer will have time to reform, and the reading coming out of that won't be very accurate. But I don't think we have that problem in current days, since all the people seems to be in a hurry, so they're always speeding. So we're fine in that regard. But the results from the actual 19 total cracks were actually it was successful. From the 15 visible cracks, 4 locations were actually actively growing. 5 of them show potential to grow, and only 6 of them were not actually growing. With this information, you know how much damage are you actually putting into the structure, and what are the locations that are actually getting most of the damage due to the ambient traffic or the rolling test. And use this information to low rating the bridge if necessary. And then we have the results from the retrofits. The first retrofit was not actually working. It actually showed that it showed that the crack was still actually growing, so the repair did not work. 2 of the other repairs, they show microplasticity, meaning that was going to grow. It had a potential to grow, sorry. And only one of them actually was fixed. Out of these retrofits, the first one was weld retrofit. The two that showed microplasticity were drill stops, and the last one was cutout, the one that seems to work. So the conclusions for this, after the study, we have that the EFS is an NDT technology that can identify cracks in the activity of the crack in real time, that it needs dynamic loading for an accurate reading, and it can verify repairs and retrofits prior to changing the load limits. And by measuring the direct damage occurring to the structures, a more accurate load ratings can be achieved.
That was clearly a crack due to small web gap.
Yes.
What was the retrofit before you did this monitoring? Could they have put some sort of plate from the stiffener to the flange and bolted it to make that a stiffer connection?
We don't do the retrofit. We actually go and verify the retrofit.
Understood. But my question is, there was another, for example, in this picture, if they had drilled the crack, for example, wouldn't that have arrested the crack? Would you then put your technology after the crack hole, for example, is put in there? Would that what this would serve? Because I'm trying to understand where there was another crack where it didn't seem like there was a retrofit. Couldn't they have just drilled a hole there and then do the monitoring, or did you have some sort of repair?
Well, there are different, for example, you're talking about this picture with the drill stops?
You had drilled a hole at the tip of the crack, wouldn't that have stopped the propagation? And then you would monitor it beyond the drilled hole? Because I've seen where you drill a hole and you go back 2 years later, the crack's gone beyond because they never really located the tip properly.
Yes.
In this case, would that have worked, I think?
Well, the first step is to know if the crack is growing or not. So if the crack is not growing, there's no point of doing the drill stop, right? Once the drill stop is done, you can actually have an option to monitor that location if that's your desire, and put a sensor in front of that drill stop to monitor that location.
Well, from an owner's perspective, you might choose to just put a rest hole and not take the chance. It depends on the redundancy of the structure and such.
Yeah, but also, like you said, it also, once you put a hole, it actually, I think 40% of the drill stops, they have proved that they do not work, that the crack will still propagate through that.
So in this case, there was nothing done but just monitor the crack?
In this one, in that picture?
One, yes.
In this picture, it's just assessment to see if the crack was growing or not. They take the damage in the bridge.
Yeah, our next presentation will get into solutions.
Yeah, exactly. We're telling you if a crack is worth of a repair or not, and also if you made a repair, if it actually worked or not.
My question is, this picture shows a short-term sensor where you have to remove the paint. Are there other options where you can install long-term on top of the paint, or?
No, you cannot install it on top of the paint. You need to be in direct contact with the metal to form the passivation layer. And the short term is just to assess what the activity of the crack. If you decide to monitor the crack, that's up to you. It's up to the owner to see how critical that location is. So you have to monitor the crack. Or there's a different concept that you can use when you use the fatigue fuse, where you can actually put the sensor at a certain length, and you would like to know when a crack crosses that line or that threshold, and you can be notified when that happens.
So I'm thinking they cannot stay permanently on the bridge if the paint has to be removed. Is that?
Oh wait, for this one, since they have to be removed like in 10 days, we just leave them like this, and we come back and take them off and repaint the surface. But when it's a long term, I think I have a picture here with the installation. Oh, there's an installation. But usually when we put the long term, we paint all over that. So we make sure that the steel is not exposed to the elements.
How do you use the data you collected to assign now a numerical load rating to the structure?
How do we use the data? Well, I think we are telling you how what kind of loads is actually making the structure to fail in fatigue or make the crack even longer. It's up to the owner how they're going to use that information to load the bridge.
So you're running different weight vehicles over it?
Yes, and you can actually have a threshold saying like this amount of weight will actually make the crack to propagate or not in these certain locations.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.